So welcome everyone. My name is Glenn Milner and I work with the Climate Risk Institute. This session focuses on climate hazards and thresholds, and I hope you'll be able to take away a solid understanding of how do we scope a risk assessment from this perspective of hazard, what does a threshold mean, and where can I go to get data around threshold values. So with that, I'll jump right in. So just walking through the table of contents now for this session, I hope to just begin by defining conceptually what vulnerability can be interpreted as. I'll then provide an example of what that means in a Canadian context for your reference. I'll then move into how climate thresholds are used in risk assessments. And then I'll spend the bulk of the time talking about sources of information to leverage in developing thresholds to support risk assessments. So just to begin, you can broadly understand the term vulnerability as existing as a gap. Now I'll unpack that a little bit, but when you think about the term vulnerability, or if you were to picture a piece of infrastructure, it's often designed, built to a particular capacity. It's able to withstand a certain amount of extreme condition before impacts or degradation can occur. So that's that blue bar here on the slide. However, we know that in real life or real life conditions can often exceed that capacity, and that is the load that that particular piece of infrastructure may experience or may receive. And so where that load exceeds that capacity, you have a gap. And that gap can be referred to as vulnerability. Now, kind of conceptually defined, vulnerability is the point at which a load exceeds the capacity, and it's that gap that we have to be concerned around when it comes to risk characterization. Now, the threshold value is the point at which the load exceeds the capacity, and that vulnerability can be far exceeding that threshold value. And so that threshold value is particularly important because if you raise it or lower it, you are representing different levels of vulnerability to a particular piece of infrastructure. Now, it's really important to understand that when we define a threshold value or a climate threshold, there are implications of that definition in a risk assessment. So when we often undertake risk assessments, I like to use the term or the phrase, begin with the end in mind. So as you're scoping a risk assessment, as you're defining your hazards, as you're defining your thresholds, what are you hoping to get out of the process? What are the end outputs that you're envisioning? Is it a detailed modeling exercise? Is it a high-level desktop study? It's important to understand that the threshold value has implications for the levels of risk that are interpreted. Now, I'll just walk through this slide here to give you an understanding or an illustrative example of what I mean. So for example, the point at which the load exceeds capacity could potentially reflect degraded service of a particular piece of infrastructure. If we were to raise that threshold value to be potentially higher or less conservative, depending on how you frame it, this could refer to a loss of service provided by that piece of infrastructure. If you were to define an even higher threshold value, that could be associated with equipment failure. And finally, if you were to define the highest value, that could be referred to as a total loss of an asset. And so the selection of that threshold value inherently carries forward in terms of the risk characterization that we're undertaking. So keep that in mind. So the lower the threshold value, the less significant the impacts may be, but the more conservative your approach to risk assessment may be. Now, what does this look like in a practical example? This is a Canadian example that looks at the number of insurance claims per day relative to extreme wind speeds or gusts. So on the y-axis of this graph here, you can see the number of insurance claims ranging from 0 to 90 per day, and you can see the peak wind gusts ranging from below 32 kilometers per hour all the way up to exceeding 90 kilometers per hour. And you can see here that in some cases, small increases in that wind gust can actually lead to massive increases in the number of claims and in this case, damage to our infrastructure. So 90 kilometers per hour in this figure, you can see all of a sudden there's almost a 600% increase above that threshold compared to wind speeds or wind gusts between 81 and 90 kilometers an hour. So it's these types of critical thresholds that we're also trying to ascertain and understand in this types of scoping exercises. So keep these types of relationships in mind. Now, it's important to also understand that there are different approaches to climate change assessments and to risk assessments. There are top-down approaches, which is indicated in blue on this slide, and there are modified or bottom-up approaches that are indicated in green on this slide. A top-down approach is often used, kind of leverages climate model data at the highest level. It's downscaled. It informs local models, local processes, hydrology models, for example. From there, model outputs inform potential impacts, and those impacts are responded to using adaptation options. On the other hand, in green, a bottom-up approach begins with understanding the system and the infrastructure first. So we can understand, for instance, critical thresholds, the ability of a piece of infrastructure to cope or to withstand extreme conditions. From there, we align those critical thresholds with climate model data, and then we can use that to inform adaptation options. And so both of these processes have a place, and it's important to understand that they have a role. However, the bottom-up approach is really preferred when it comes to really trying to understand how your system is responding. Top-down approaches are more frequently used at higher level scale assessments. So across an entire country, for example, or across an entire portfolio, where you're unable to necessarily dig down into the detailed thresholds and response. And really, it's important to understand that the selection and identification of climate threshold and threshold values to inform risk assessments is an iterative process. So for example, if you were to envision a risk assessment team who understands the infrastructure systems, they would need to work collaboratively with climate experts, whether they're climate modelers, climate data analysts, to inform not only what the thresholds or hazards of concerns are, but also what are those threshold values we want to run through our analysis to inform our process. Now, when it comes to developing thresholds, there are many sources of data we can go to and kind of pinpoint to really understand what are these values that are most relevant to our systems. There are things like codes and standards that may be referenced or referred to in infrastructure. There are design information. There are oral histories and experiential information by staff, by managers. There are operational experience or site visits, for instance, for a particular piece of infrastructure. There are forensic analyses or history of a particular asset, if it's already been impacted. And finally, and probably most critically, there is professional judgment. And so all of these are sources of information that you can think about when trying to understand, A, what are the hazards of relevance to my system, and B, what are those threshold values I want to dig into, and how can I go to these different sources to identify those data sets. The key message here, though, beyond begin with the end in mind, as I talked about earlier, is that always try to complement one data source with multiple sources of information. So the use of kind of one and done data sets or data source may not most accurately or appropriately reflect reality. So we want to try to corroborate that or use multiple to complement and make sure we're ground truthing to the extent that we can. This is just a best practice, and a good example is to use professional judgment in combination with codes and standards or with a different source of information. So I'm just going to walk through a series of these data sources now and talk about the pros and cons of each. I'm hoping by the end of this session you have a good understanding of not only where to go to get data, but also what the benefits and weaknesses of some of these are. And so beginning just at the most basic, codes and standards are often well documented, which is a benefit. They're typically scientifically defensible in general. The weaknesses, unfortunately, are that they may not have actually been used in design. As infrastructure is built or the design information gets fed into the process, safety factors may be applied but not well documented, for example. And of course, it may not accurately reflect or factor in kind of wear and tear of infrastructure over time. And so the key message here, it's a good starting point, but requires additional confirmation and validation. Moving on to design information itself, the benefits of this is that it's often based on much more robust engineering. It's also easy to reference. It references codes and standards, perhaps, or the basis for those calculations and design information. On the con side, it may not be widely available. It may not have actually been used to engineer the design, and what is designed may actually not be built. If you think about what actually exists in the ground over time, an institutional loss in memory, things can change, and it can be hard to pinpoint exactly what is there now versus that specific design information that was produced originally. So the benefit or the kind of takeaway for this source is that it identifies the basis for asset design and can be helpful to corroborate other sources of information. Another source of information to consider are rules of thumb. And the benefit of these are that they're often based on professional judgment being used at the time of construction of a piece of infrastructure or at the time of design. The weakness is that they're not often well documented. So we often have to have a lot of conversations and particularly try to find those who understand the infrastructure best, which can be challenging over the long term. However, these do most or more accurately reflect as-built conditions, which is important. So if there was a safety factor or a rule of thumb built in, it's important to have that conversation.